Is there information about what is happening or about my thing? Okay, so what is the idea? Is he starting to use these equations, which are the pulse of wave frequencies on the pulse of wave frequencies, right? Oh, and it starts to determine from it or figure out where the peaks come from. This section delves into the origins of the data, exploring the various sources from which it is derived. It also examines the circumstances under which issues may arise, providing detailed information on potential problems or any aspects that might be connected to the current idea. Furthermore, the discussion extends to the concept of pulse of wave frequency, specifically focusing on how it is calculated by subtracting the minimum frequency from the overall frequency. This principle is crucial in understanding the dynamics of wave behavior and its implications in various fields. By analyzing these elements, we gain a comprehensive understanding of the data's background and its relevance to ongoing discussion. Future parameters, which are essential, are those that can be used and can show the required diagnostic results depending on the case, the specific situation being worked on, and circumstances. In various scenarios or conditions, for instance, in the case of the pulse of wave technique, you specifically need one crystal. Regarding continuous wave, we used to say that it is essentially a prolonged ringing sound, unlike pulse of wave where you get a pulse, which means it's a short pulse. So, if the Q factor is considered important, then for you personally speaking as an observer or analyst in this field of study, the bandwidth is large and has an accompanying metric. In the case of pulse of wave, unlike continuous wave, you can determine the location or area from which you want to perform the sampling using something called Doppler gate. You can precisely define the location from which you want to work and from which you will send your signal. You can also determine the velocities of the plot flow within your vessel, as you can see in this way. The pulse you are sending, if the pulse has something called, as we discussed, the pulse rate frequency, which is PRF, if this pulse rate frequency is low, the same idea occurs with aliasing artifact. This means that the frequency of the pulse you are sending is lower than the speed or lower than the flow speed of the RBCs themselves. In this case, the signal you receive will have some issues in the data. This causes aliasing artifact, which manifests as a distortion. You will find that part of your peaks starts to appear downwards in relation to your spectrum. This is called aliasing artifact, and it is beneficial to increase the pulse repetition frequency or increase the frequency of the pulse repetition, the rate of the pulses being emitted. This is different, of course, from the situation where you are working on something that does not show this effect. What about the plate? How is it? I can't see the ones that are present, okay? This is the same view shaped like this. There is something called tissue Doppler imaging. We will talk about the topic of blood flow. If you want to see the motion of the myocardium instead of the blood flow, you perform tissue Doppler imaging or flow imaging. It's the same idea. For example, you use the motion present in the movement, and it is done in the same way as the movement of the metro, for instance. So how is this done? It is done in the same way. In Doppler imaging, you choose, for example, the volume or the area where the motion you want to analyze is located, and you define your target. This indicates that you want to measure at a specific location or area. This is, of course, done using the pulse which represents the systolic pressure, while the bottom, or the existing part, represents the diastolic pressure, which then starts to be defined. All the parameters he wants to work on, whether they are related to the cardiac muscle, or if he checks whether they are present or not, or if there is something that occurs before another in a specific sequence, or if something happens in a certain way related to the cardiac function. Doppler imaging can potentially demonstrate the desynchrony that may be present in the contractility process. If the machine produces an anatomical image, which is a 2D image, at the same time it performs color Doppler, or the color representation. If it gives you the color flow or the plot flow, I call this duplex imaging. Like color Doppler or blood flow, this is called duplex imaging. If the machine shows 2D imaging and provides you with color and spectral tracing, in this case we call it triplex imaging. The term duplex imaging means that I have Doppler and I have low brightness mode, in case you or the color mode, which is the B mode. If you have it, you can produce the 2D image, color, and spectral, meaning you can also extract the analysis of the volumes and all these parameters we talked about earlier. So I call this triplex imaging for me. Now there is something called harmonic imaging. What is the topic of harmonic imaging? They said in America, he is carefully trying a very certain experiment in detail. He has started and meticulously to send, and he is thoroughly receiving what is coming back to him. So it stopped, and eventually after a while, or after the stop, it was abundantly clear that there is a return from the existing tissues. That's why it came back to me. They said there was a certain occurrence between me and what exists in the body. I did something called, what does it mean? I have my thing looking like this. There is a part in it, and there is a part in it. This compression part for me is the high pressure, and the part that is the reflection is the weak part for me. The part that tells you the result of the pressure occurring in these tissues or the particles present experiences oscillation. This oscillation does something. It changes the frequency. You are supposed to have it return again after it happens with it. They found that instead of it being shaped like this, meaning you have it and the shape is equal, there is no problem. They found that the shape of the peak became like this. In part of the peak, there is a non-linear effect occurring. What does non-linear mean, and why does this shape happen? It is due to the fact that in this part, there is high pressure or compression occurring, which affects the interaction between the particles present. This leads to the particles creating oscillations. These oscillations result in ultrasound pulses or reflected pulses. These pulses come from the tissues with a frequency that is double the frequency being sent. For example, if I send ultrasound pulses at a certain frequency, say 2 megahertz, I receive frequencies of 4 megahertz, 6 megahertz, and 8 megahertz. This is a result of the interactions occurring in the tissues, which cause changes in the properties of the tissues themselves. The oscillations present in the tissues or particles create ultrasound frequency, doubling the frequency. So when I send 2 megahertz, I receive the same frequency, but it is not just that. You will do tissue imaging or harmonic imaging. You will completely avoid filtering out at 2 megahertz and take the 4 megahertz to receive. This is what you will use for imaging, and this is what you get from the tissues below. So how does this happen? In fundamental imaging, in regular imaging, you send ultrasound pulses that undergo attenuation due to interaction. They go down to a part and get affected, and when they come back, you receive them with the transducer. This is what happens in regular work. But they told you no, in this case, the pulses are actually coming from what is present here. It will not experience attenuation. It will only experience attenuation in one direction. It's as if you are getting a very strong signal, which starts to show the image better, better, and better. This improves the image quality. And this is the difference between tissue harmonic imaging and fundamental imaging. If there is tissue harmonic imaging, it is better for improving the same idea. The difference is clear between them, and for you, it is higher in quality. You mentioned that the higher frequencies generated at tissue interfaces traveled a shorter distance, resulting in a higher signal intensity. Now, there is something called the reverberation artifact, which we will discuss in the context of artifacts. We will talk about the signal that you receive. For example, this is the signal you transmitted in conventional or standard imaging, and this is the signal you received. Both have the same frequency, but the amplitude differs. However, in the case of harmonic imaging, this is the signal you transmitted, and this is the signal you received. So now you have a different frequency. Both frequencies are combined, meaning that the signal you receive will contain the fundamental frequency as well as the new frequency resulting from interactions. So what you have is the transmitted signal D and the received signal. In a normal case, you won't actually receive the harmonic signal because either it hasn't arrived yet or you won't be using it. So you perform filtering for any frequency other than the frequency you transmitted. For example, you transmitted at 2 megahertz, and there is a certain bandwidth. This is the bandwidth in which you receive your frequency. The frequencies you receive range from this to that, and this is what you are receiving. Now, in the case of using, what is the dye that I use? That does the same technique and does the same job. When I come to dye it and start doing imaging, I do the same work. What happens is that it does something called, what does it do? Microbubbles in contrast media mean that contrast media consists of microbubbles. I inject these microbubbles into the partition, and their shell is either a lipid shell or a protein shell, and they are hydrophilic so that they can be water-loving. Hydrophilic means they are water-loving, while hydrophobic means they are water-hating. This allows them to move in the bloodstream. The ultrasound pulses that are incident on them create the oscillation we talked about earlier. This oscillation then creates something called resonance, which produces a frequency that I receive, giving me a reflected signal with higher intensity. This highlights the areas where the contrast media is present with higher intensity. In the imaging system or imaging modality or ultrasound, there is something that tells you that this is your received signal frequency. For example, this is the fundamental frequency and this is the harmonic frequency, which is 2F or 4F. I received the fundamental frequency and received other frequencies coming from tissues. So what should I do? The important thing is to filter this out and only receive this. So what is the advantage of this? It is said that when you filter this out, you are receiving something with a different frequency, but when it returns to you, it will not behave like the fundamental frequency that you transmitted because it is going back and forth. This is number one. Number two, the artifacts that were appearing and causing problems will diminish. Why? Because when you were transmitting the standard fundamental frequency, it interacted with all the tissues and objects present in the patient's body that received the same frequency and returned the same frequency. So you have things creating noise. The unwanted artifact will be removed with filtering or by applying frequency filtering to the standard frequency that I don't want. All of these artifacts are coming to you in your standard range, which you already sent. Do you understand what I mean? So basically, the frequencies coming from those choices you want to detect are precisely the ones you'll receive, and then filter out all other frequencies originating from these artifacts. This process will significantly enhance your image quality overall. This is typically what usually happens. Both transmitted signal and received signal spectrum undergo processing for image display purposes. This means ultimately that this interference will indeed be removed. This represents the signal that went out and came back again, resulting in attenuation in conventional imaging. Here, the signal comes directly from its depth, so the attenuation is less, making the signal stronger. This in turn improves image quality. For example, there are some artifacts like the side lobe artifact. This is the primary imaging, and this is harmonic imaging. You can see where the pixel came from. It came from the primary because, as you said, you sent the standard frequency for all the tissues present, so it returns at the same frequency. Thus, you have removed the artifacts from your image, enhancing the image quality. This obviously increases diagnostic confidence, distinguishing between renal cystic and solid hepatic lesions, and improves pancreatic definition. It also allows for the distinction of simple from complex renal cystic lesions, as seen in the images on the right, which are harmonic imaging, clearly showing the difference from conventional imaging.
I told you, but just to clarify, we will present in harmonic imaging the frequency that returns from the objects, which is different from the fundamental frequency. It will be higher than the fundamental frequency that returns. In terms of intensity, the intensity is lower, but keep in mind that the intensity is lower than what was sent. So, look, you sent it here, like this.
But let's assume I'm dealing with the fundamental. Here it is going large, right? It has undergone attenuation, correct? So when it returns, it will return smaller. Are you with us, doctor? It returns with a small amplitude because it will undergo attenuation. However, what returns from the echo is actually larger than it. Do you understand? I mean, what returns from the echo, which is the harmonic, returns with higher intensity and at a higher frequency than what? Not from the primary, which is the original signal. It has the same frequency as the primary, right, doctor? Okay. There is something called compound imaging. You perform an imaging process that involves different operations. If you take a single view or angle for the transducer in this way, you get an image like this. If we remember, some of the rough surfaces where interactions occurred. With ultrasound pulse, it was giving you a pulse, and this pulse appeared as if it were noisy on the image. This means you will find that the image looks a bit noisy in these areas due to what? Due to the scattering that occurred, which is no longer referred to as speckle scattering. It's not isotropic at all. First, number one, the significant thing that happened here is that when it came or appeared, there was a thief or something like that, as you can see. So, what is the result? You have here an angle, and someone told you that we will do something. Remember the topic where you were taking, for example? If I have this shape, and at the transducer, you are moving in the direction from the left side to the right side. You are moving here, creating focal points here, then covering here, and then covering here, as if you are covering your field of view from left to right. This is what beam steering is about. You are taking different angles, and the same idea applies. You are capturing the same image or the same thing. So you are enhancing the image quality that comes out. Okay, good. The problem with this story is that your frame rate here allows you to reduce the number of frames you will create using different angles to obtain a single image. Therefore, you cannot provide many frames using different angles. When you compare the frames with the different angles, you find that the frames are fewer for you. And this is one of the existing problems with the different angles. Of course, these are options or specifications available on the ultrasound machine, whether it is harmonic imaging or compound imaging. If they are present, they should enhance the image quality during the imaging procedure. All right, come here. The topic of microbubbles or contrast-enhanced ultrasound. What do I want to do? I want to inject contrast media. For example, when I was in the city, we were injecting a dye that had a high density to create high attenuation of the X-ray beam and increase the difference between the dye image and the surrounding background tissues. Here, the same idea applies. You want something that you will inject and that will circulate inside, so its diameter must be smaller than that of the existing structures to ensure safe passage. If it gets stuck, it could cause problems for the patient. The idea is to keep it present for a suitable period so that during imaging you can detect signals. It must be a strong reflector for ultrasound, meaning that when exposed to an ultrasound pulse, it will provide a high reflection to illuminate the area well, allowing you to identify if there is blood flow, for example, whether there is a tumor or some issue you want to examine the margins of a specific tumor or something. And if there is blood supply to that area, you want to see it better. Therefore, you use the contrast, which is particularly useful in cardiac cases. In summary, in certain specific cases, I don't have a comprehensive background on whether they are used widely or not, but through my extensive readings, I have seen that they are used more frequently in cases where they appear significantly brighter than regular ultrasound images without contrast. So what happens is that when you administer them, they use something called a specific diameter, which is considerably smaller than the diameter of the regular ones, and they are surrounded by a hydrophilic material to help them move efficiently in the bloodstream, having a different set of unique properties. In some structures, it is said that they help to remain present for a long time, while in other structures, their washout is quick. This depends on the different companies that manufacture the available contrast media. The idea is that when you expose these microbubbles to ultrasound, a phenomenon occurs called shrinkage and another called expansion. What does shrinkage and expansion mean? As you can see, the bubble itself shrinks and grows, shrinks and grows. Shrinkage refers to the contraction, and expansion refers to the extension. It was mentioned that the expansion that occurs there is no expansion or contraction, meaning that there is an initial expansion, and this occurs slightly due to the pressure applied to the microbubbles. This pressure is what causes the behavior of the microbubbles.